introduce you, okay?
Sure. Mhm.
Uh, Welcome everyone. Uh, Today, our speaker for Higher Structures seminar series is Kadri İlker Berktav from Bilkent University. He will tell us about his work on constructions of contact-derived stacks. Please, İlker.
Okay, so thank you for the introduction and having me here. It is always a pleasure to be part of this event. Um, okay, uh, so today I'm going to actually discuss a sample constructions of the so-called contact derived stacks. But of course, before that, I'm going to introduce, several terminology, notations, and maybe some key facts from, especially derived symplectic geometry. So let me just briefly start with some notation. Okay, some notation. So there will be some details. So I'm going to skip some details. So unfortunately, but at least let me fix the notation. Okay, some notations. So for us, so we are going to actually study as an underlying topological space. So drive stacks. Okay, so X will be a drive stack. So by which I mean, so it's a kind of a pressheaf from the infinite category of CDGAs, non-positively graded, and we have a base field, let's say characteristic 0 and close, and to the infinite groupoids. Okay, and plus some extra data, descent condition, but mostly we consider just this pre-stack part. So in total, it's just a sheaf of infinite groupoids, right? So therefore, when I say a drive stack, I mean the functor, let's say just the functor in this form, okay? Infinite groupoids. And what else? When we say a point, a point in our stack, so P in, let's say P in X, so I mean P is a kind of an element of XA. Okay? So therefore it's a kind of a called A point. And so if you have a point like that, so you can express your point or you can consider the point as a certain map, right? From spec A to X itself. So when we say a point, we consider the following map like this. So this is really how we, use Yoneda lemma actually. Okay, so when we say a point, we mean a map like that. Of course, there is no special condition on this map. If this is a kind of an inclusion, I mean, let me just say the open embedding, then we call, instead of just drive stack, we just consider a specific drive stack and we call them drive schemes. When this map is open embedding, it means that, and when you have really a notion of an open cover around any point, open affine covers, and in that situation, we just say, instead of drive stack, we just say drive scheme. Okay. So these are some basic notations I'm going to use very frequently. And what else? Of course, for any drive stack, you can define the Deram algebra, okay, or the Deram complex, which is essentially defined by using the infinite limit. So I mean, this is like a limit of the Deram algebra. So you have the CDGA, and you consider you consider A element CDGA like this. Okay, so you just consider the infinite limit. You consider the limit in the infinite category of CDGAs. Okay, so this is how we define the Deram complex. So likewise, you can define, so similarly, so it's a similar definition will work for the structure sheaf, or if you consider the quasi-coherent sheaf on X, you can define them by using this by using the CDGA. Okay, you can consider this spec A or this point P, and this is how we define all of these objects for arbitrary X. And also you can write another important maybe observation. So when X is an artin, so X is artin, so artin stack. So what does it mean? It means essentially if you go back this map, remember this, we use a color here, this map over here, the red one. So if this map is not, okay, in general, it's not an open embedding, but sometimes it may have still nice properties. If it is a kind of a smooth, surjective, smooth of relative dimension, n, let's say, then in that situation, we call this derived stack artin. Okay, so essentially, when X is artin, it's a very nice derived stack, but sometimes it is not enough. But let's say it's nice enough. So in that situation, you can write deram X as, you know, in a kind of an expected way. So if you remember the classical situation, this is a kind of a sections, right? The space of sections uh, of the cotangent complex like that. You consider the, you know, you consider the symmetrization. Okay. So and also another maybe some terminology. So of course we want to define, if you consider the PTVV's, you know, symplectic geometry, we want to define geometric objects like forms and symplectic structures. Okay. So in general, we use the following notation. So Px, so I use n. So it means this is, let's say, let me just say the space of P forms of degree n. But actually, it means that, it essentially means this is the space of, so as in the classical case, you know, we want some kind of cocycles, right? So these are n cocycles in the Deram complex above. Okay, so something like that. So P X, and we have some extra shift here. Okay, so this is n cocycle with respect to what? With respect to the internal differential D. So remember, we will have two differentials. So D total, D plus D Deram. So therefore, with respect to this internal differential coming from, you know, the differential of your, let's say, the CDGA, you know, we are dealing with CDGAs here. So this induces a suitable internal differential. Okay. And what else? What else? Another notation is the closed forms, of course. So this is, let's say, the space of closed P forms of degree n. Okay. So therefore, in the same logic, now these are kind of the space, the collection of n cocycles, space of n cocycles, but now in the following complex. So instead of Deram, we consider this. So somehow, so I'm going to write down. So let me write it down first, and then I'm going to explain. So, and this is for D total, not with respect to D, but now with respect to D total. So what does it mean? It means that if we consider a typical element, for instance, from here, P forms, n-shifted P forms, another terminology, equivalent terminology. For instance, it means if, for instance, you have a typical element from here, okay, so I just suppress the space, the underlying space. It means that this is just a D-closed element. So the D closed element of this Deram complex. And the weight weight P, but the cohomological degree P plus N. Okay, weight P with cohomological degree P plus N. But if you have, so let me just use P here. So if you have omega from P close and degree N, it means that, remember, this is a cocycle in this product, right? So therefore, this omega is like a formal power series. So you have omega 1, omega P, P plus 1, and it goes like that. Okay? So this is a typical element. And any arbitrary element here, for instance, omega I inside, this has weight Q, but cohomological degree still P plus N. Okay? And therefore, they satisfy. So it's like this. So the first element here, it's essentially D close. So therefore, we call the first element here the leading term, which is because of this condition, this is an honest P form here. But of course, there are other relations because we want D total closeness. Remember, we want D plus Deram closeness. But it means that this omega P, it's almost Deram close, but there is then kind of a correction term, okay, like this. And you can define infinitely many relations like that. So therefore, the meaning of this D plus Deram closeness for any I, this thing I plus 1 is 0 for all I bigger than P. Okay? So therefore, it's like the other terms here, except the leading term, the other terms are like correction terms, okay? Homotopy terms, higher terms and correction terms. So these are general notations. We are going to some terminologies from derived symplectic geometry. Maybe a couple of more. So if you look at carefully, you can really see a natural map. That X is a natural map from closed P forms of degree N to P forms of degree N. Of course, these are kind of infinite, power series. And the first term is the leading term, given like that. Of course, you can just project into the first term, right? So therefore, there is a natural map mapping to the leading term. And what else? Maybe an important result from this PTVV's paper. Actually, this space, P, X, N, has a very familiar characteristic, actually. If you remember the classical setup, in the classical setup, the P forms are like sections, right? Sections of the cotangent bundle, I mean, the exterior power of the cotangent bundle. So same kind of result will apply here. So we have a nice result like this. So this space can be seen as the sections of this exterior product of the cotangent complex shifted by N. So the right-hand side means the section, okay? A space of sections like this. Okay, so this is a desired property. This is what we see in the classical setup. Of course, it's a mapping space in the infinite category of quasi-coherent sheaves. So therefore, we have this natural characterization, for this space. Okay. So therefore, for instance, if you consider a very typical, for instance, two form of degree N, let's say, you can really write this thing by using, by duality. You can view omega like, in a very usual way. So you have this tangent complex. So it eats two vectors, if you remember the terminology from the usual differential geometry, and it splits out a function, right? But of course, we have the structure sheaf, we have the shift. So therefore, this really eats two vector fields in quotation marks, right? So by duality, therefore, you can see any two form like that. And this implies, by using adjunction, this induces a very typical map from the tangent complex to the cotangent complex shifted by n. And therefore, if you want to define symplectic structure, you require this final map, to be an equivalence. So in that category, the infinite category, the equivalence means the quasi-isomorphism. So therefore, a quick definition, n-shifted symplectic, n-shifted symplectic structure on X means actually you have, as in the classical setup, you have a closed 2 form of degree n. Of course, it has a kind of a leading term. Sorry, P is 2 here. So there is a leading term, and there is a map induced by the leading term here. I don't know why, I'm just using P. And we want this thing, the induced map, is an equivalence. Okay? In this setup, it is just a quasi-isomorphism. And this condition is called non-degeneracy. Non-degeneracy condition. So same kind of non-degeneracy condition, is happening in the classical setup, right? So if you remember the classical symplectic geometry, symplectic form means you have a closed 2 form, and the induced map between the cotangent bundle and the tangent bundle, must be an isomorphism. So in a very statement in the same spirit, but in the derived context. Okay, if you're not familiar with these things, so this is the general idea. Of course, there are many interesting results in derived symplectic geometry. Maybe you can even introduce, Lagrangians. You can discuss Lagrangian intersection theorem, mapping stacks. You can discuss certain shifted symplectic structures on mapping stacks. And there are also nice results regarding Darboux theorem, local results. So there are many interesting results, but in this talk now I'm going to discuss the contact structures. Okay, there are many interesting details from the symplectic geometry, but for our purpose, these definitions and notations will be enough. So the similar kind of definitions for contact structures. Okay, so how can we discuss contact form, contact structure in that derived context? Of course, maybe I should remind you the classical picture. Classically, the contact structure on a manifold means a contact structure on X. Now this is a manifold, an odd dimensional manifold, right? So we mean, so it actually consists of the following data. So somehow you need a distribution, right? A rank 2 distribution of the cotangent, the tangent bundle. So therefore, for each point, you have a kind of a splitting like this, okay? Something like this for each P. So therefore, this part is kind of rank 2n dimensional. So this part is 1 dimensional, and of course, this is 2n plus 1 dimensional. So existence of this psi, the rank 2 hyperplane smooth tangent hyperplane distribution, okay? Existence of this thing. And of course, plus some non-degeneracy condition, because locally, you can express this thing by using the kernel of a one form, right? So let me just write something like this, it's clear from the context. And locally, so you have a local one form, your kernel, and what we want to consider the induced map. Now you have a 2 form and you have the induced map between, cotangent space and the tangent space is non-degenerate when we restrict to this kernel, is non-degenerate. So this is the non-degeneracy condition. So it means that if you consider your distribution and you look at, these vector spaces like this, now this pair for each P is a symplectic vector space. Symplectic vector space for each point. Okay. So therefore, eventually, you have the following splitting. So somehow locally, locally you have this kernel alpha, okay? You have this map to the tangent bundle, and then you just consider the cofiber, right? So Tx over kernel alpha, and this is your one-dimensional part. In general, we say the Reap vector field, the vector field generating this rank 1 part is called the Reap vector field. But this is actually the cofiber. So you have a kind of an exact sequence like this, and this part is your cofiber. Okay, we are just looking at the quotient. So therefore, this is more or less the the basics of contact geometry. And there are, of course, many nice results. You know, Darboux theorem, similar results in this contact geometry, like Darboux theorem for contact structures, neighborhood theorems, Legendrians. They are like a counterpart, odd counterpart of the Lagrangian structures in the case of symplectic geometry. And what else? Symplectification. I don't know, many others. Okay, there are other nice results in contact geometry. So let us try to translate this data, by using our dictionary I just introduced above. Okay, so we are just translate this information in the context of, derived symplectic geometry. So therefore, let us define n-shifted. So our purpose is n-shifted contact structure on now X is derived stack. Okay, so let's try to define this. The first part of the definition is first we define the pre-n-shifted contact structure. And actually it consists of the following data. First of all, you need a shifted line bundle. Ln. Okay, I mean, you have just locally free sheaf on X. So this is your line bundle, shifted line bundle, and a morphism. So we want a morphism. Call it alpha from Tx to this L, shifted line bundle. And this is a morphism in Q co X. Okay, so for the pre-shifted data, so here the pre part, so we want this information. Okay, so these two things is the part of the data. So let's see what's going on. So as a notation, I'm just using, when I use this kind of notation, it means we are discussing the pre-n shifted contact structure. And we have an important remark here. The remark, actually, you can consider the following. So consider the following cofiber sequence. Okay, actually, we have K, Tx, and Ln. Okay, so this is our alpha. So the left-hand side is cocone of alpha. So it's like kernel, okay, but the homotopical version. And since this is a fiber cofiber sequence, actually, since Q co is a stable infinite category, every exact sequence is co-exact. So therefore, this guy is just the cone of this map. Okay, so therefore you have this kind of relation. So therefore, this L really, so you have kind of quotient, right? Cone is just the homotopy quotient. So the homotopy quotient of this map, the image of this map of the tangent complex gives you some rank 1 locally free sheaf. So this is really, if you remember the original classical definition, we are just encoding this picture over here. Okay, because we have this sequence. Remember, the splitting locally splits. And actually, we have this kind of locally splitting behavior. So in general, we are going to be interested in negative shifts. So for negative shifts, and let's say X is just drive scheme, in that situation, this triangle or this exact coexact sequence, this guy here locally splits. Okay, so it means that locally, for instance, over some spec A, what does it mean? You have a point, spec A, and when we say point, we understand this map. It means that when we consider this pullback, right? So you have this splitting. Okay, but actually, when you have a dry scheme, this map is nothing but some kind of open embedding. So these are just restrictions. Okay. And maybe one more. Of course, this guy has kind of a Tor amplitude. So it's a kind of a complex, right? With Tor amplitude like this, minus n. So our n is shift. You know, the tangent complex is in a positive direction, right? The cotangent complex has a Tor amplitude in negative direction. And this one is concentrated in degree minus n. Okay, so this is just constant. This is just because no, it's just a line bundle, right? So everything actually concentrated in degree 0, but we have this n shift. So therefore, this shifted line bundle is just something concentrated, a complex concentrated in degree minus n. N is negative number. Okay. Okay, so with this observation, the second part of the definition, of course, we need to introduce some kind of non-degeneracy condition. So when we say K shifted, I'm sorry, I was using N. So anyway, so K shifted contact structure on X, we mean two things. First of all, we have this pair in the sense of above, this pair, line bundle and the map. So this is the pre-data. And we have some kind of non-degeneracy condition. We need to introduce non-degeneracy condition. Let us introduce. So it's a condition like this, locally on X. I mean, we are just considering the trivialization of L. Okay, so where L is trivial. And then let us consider the induced one form for the induced one form. Let me use the same thing, alpha. So we have this induced one form of degree K, right? We consider the following map. Of course, we have the natural map. So, of course, we have this D deron alpha dot. Since this is a two form, right? So we have this natural map. But of course, we are not saying this is non-degenerate. Instead, we consider this part and this part, dualization. Remember, this map we call kappa, and let's say this is kappa dual. The map over here, let's say we impose the condition that the map over here is non-degenerate. So therefore, this D deram alpha restricted to K, this is our notation, but we actually mean the following map. Kappa, maybe I should be a little bit careful. So some K shift here. Compose D deram alpha, the induced map. Compose kappa. Now this is a map from, our K to K dual with shift K. Okay. This map. Now we want this map is an equivalence. So therefore, this is kind of quasi-isomorphism. Okay. And we say, actually, for short, we just say, Okay, D deram alpha is non-degenerate on K. When we say something like this, we mean the following. I mean, we mean we mean this map is an equivalence. Okay, so this is a short way of saying this is something like that. So now this is our definition essentially. So we just translate the classical data to the context of derived geometry somehow. Oh, by the way, I changed this definition several times. I really thankful to the anonymous referees. So I changed it a lot, and finally, I guess this is the final version. So I revised some of the manuscripts accordingly. So I hope this is the nice and the simplest version because the previous version was a little bit complicated and there are some issues. I hope this version seems relatively easy to capture. And also it is possible to strictify this definition. For instance, if you're just working locally, for instance, for K is negative and X is just a fine derived scheme, then actually the K-shifted contact data can be strictified. Okay, you can strictify the contact data, by which I mean we really consider this thing as kind of an inclusion map, and instead of the tangent complex, we consider derivations. So these are just deals of the Kähler differential like that. By the way, I'm just assuming A is a special kind of CDGA, a cofibrant CDGA. So it's like, so we have kind of a model categorical structure. So we consider cofibrant replacement. So let's say just A is just cofibrant CDGA. But these are kind of very nice CDGAs. These are just kind of free algebras. Their generators are finite, so you can really write down some kind of explicit representations. So these are nice. So such that, so let me use cone of this map is just the co-kernel. Okay, we are just strictifying the structure. So, so long story short, instead of cones and co-cones, you can use co-kernels and kernels. This is what I'm trying to tell you. Okay, and the same kind of stratification. So this K, your distribution is just directly the kernel alpha. Okay, and we want alpha D deram alpha is non-degenerate on the kernel. So what I'm saying, instead of using the homotopy kernel, you can use the strictified versions. Okay. So let me give you a motivational example, and let us then consider more complicated ones. For instance, this is a motivation coming from the classical setup. Actually, in the classical setup, we have cotangent bundle, right? So the cotangent bundle has a canonical symplectic structure, and when you consider the projectivization of the cotangent bundle, it turns out to be a contact manifold. Okay, so somehow we are going to mimic the same procedure over here. For instance, let us say our shift is something odd. Let's say shift is -3. But in general, you can do that for any odd shift. Okay, and let's say our A is a free algebra over A0. Okay, and A0 is just a smooth K algebra with the following coordinates. Let's say you have degree 0 variables. So the meaning of smooth K algebra is the following. So you have, let's say, finite many degree 0 generators such that the modulo of Kähler differential over here is actually spanned by these things. Okay, so therefore, for any point, this kind of gives you a kind of a coordinate. So for any P in spec A, okay? Which means for any point, because remember, so points are, so if you consider any drive scheme, if you consider truncation degree 0 level, points are actually sitting there. So the points are just classical points. So therefore, in the degree 0 level, for if you consider truncation, you have the actual scheme, right? So therefore, any points are in this spec A0 over here. So therefore, these coordinates are kind of étale coordinates, okay, for P, acting like that. So these are really like a coordinate chart from spec A0 to A1, oops, 0, here we have K. Okay, so it maps P to its coordinates. Okay, so these are like affine coordinates. But of course, you need to list the other generators because A itself is a kind of a free algebra generated by the following variables. So let me write it down, the degree 0 variables one more time over here. And we will have degree -1 variables. Let me say that much. And also, we are going to use, I mean, different letters for some other technical reasons. We are going to see. And finally, the top degree, -3, M0. Let us choose like that, okay? But if you look at carefully, these numbers are the same because eventually we are going to pair these variables, okay? So these are list of generators in each degree, 0, -1, -2, and -3. And now let us try to projectivize. So what does it mean? Somehow you need to consider the following action, GM action on spec A. Okay, usual scaling. So it's GM here is like multiplicative group scheme. Okay, so it's like an affine line without the origin. So there are kind of non-zero so invertible elements here. So if you consider the action, and then you can consider the following quotient stack, which is by definition, this is just the colimit of the following diagram. So you have spec A. Of course, you have two natural maps. One of them is the projection map. The other one is the action itself from spec A to GM. Right? And you just keep writing the same diagram. So spec A times now GM square, and it goes like that. Okay. And the colimit of this thing is the quotient stack. Okay. So using the GM action. So it is like projectivization of the cotangent bundle, if you like, if you want some analogy. And therefore, you have the natural quotient map from spec A to spec A quotient GM, a natural scaling action. Okay. And we have a nice fact about these things. If you want to understand the quasi-coherent sheaves on this quotient space, okay, these are kind of, so there is a nice relation. These are almost like the quasi-coherent sheaves of the spec A, but we consider the GM equivariant ones. Okay, so these are GM equivariant quasi-coherent sheaves on spec A. So what does it mean? Because here you have some projection and action maps. So somehow if you look at the pullbacks along these maps, they must be compatible. So the GM equivariant sheaf means if you have some, it means you have some quasi-coherent sheaves on spec A such that under the pullback of action and the projection map, just look at the diagram upstairs, these are equal, but plus some more coherences. Okay, but more or less, this is what it is. So long story short, we have a kind of we are going to use the homogeneous coordinates. Okay, this is what we are going to do. So just consider the homogeneous coordinates. Remember the coordinates for the point. These are homogeneous coordinates for P, in the quotient. And then, of course, you can change your representative, right? So by localizing A, if you need to localize A by just inverting, let's say, the first variable. Okay, we just introduce the inverse of the variable by hand by inverting x10. Okay, and then by using this, divide all other variables, and obtain a representative like that. And by abuse of notation, I was just going to use the same kind of, uh, variables here. Okay, so you can obtain a representative. So divide each by this particular choice. Okay. Anyway, so you obtain a representative and then for the image, you get another set of variables. So now you have these guys, and you have -1, all of these, and -2, and finally -3. And now this variable, we have to be a little bit careful, but now you can combine the other variables and you can get an element in this form. So let me write down. So let me write over here k, and I'm just combining, I'm just kind of behave this special one as a kind of a distinguished variable, plus I'm just using top and bottom degrees. So here x0j, b deram y -3j, because I want to obtain degree -3 elements, right? This is how you can obtain. So this is degree 0, degree is -3, so total degree is -3. And of course, you can use the intermediate variables from j1 to m1. So which one? -1, y -2. Okay, something like that. And k here, I'm sorry, k is just -3. So anyways, so you obtain an element of this guy. Okay? And eventually you can show that this primitive element is your contact form. Okay? So this is primitive element. Of course, there are many other things to verify. For instance, you can show that, that if you consider this quotient, and this turns out to be some kind of a complex, concentrated in degree 3 minus k, so degree minus k, and actually generated by, as you may guess, this one. Okay. So this is a vector field of degree 3. And if you go back, I mean, and use this recall, you can show that this alpha, so using recall, it will imply that you can get k-shifted. So I skipped the details. I mean, if you are curious, you can check the paper. So contact structure on spec, something like this. So somehow you can produce something like this, a primitive example. Maybe more interesting example. you can do, this is called the shifted one-jet stack. Okay, this is again, we are going to mimic the classical setup. In the classical setup, if you have a cotangent bundle, you just consider the trivial line bundle. Over that one, and it turns out to be what we call the jet bundle. Okay, and the jet bundle will have a contact structure. Okay, so therefore, what we are going to do, we just consider the cotangent stack, n-shifted cotangent stack, and the direct product with, n-shifted affine line, if you want. So it's a kind of just affine line, right? Co-represented by the polynomial on a variable in degree minus n. So this is like an affine line, but we have a shift. So you just consider this pullback diagram. Right, this is just point. You just consider this pullback diagram, and the resulting fiber product is called the shifted one-jet stack, what we call. So the notation is, let me use this notation. Okay, very similar to the classical setup. Now, what we are going to do, of course, we are going to use some important properties of this n-shifted cotangent stack. Right? So if you check the literature, you can easily see that this thing is actually n-symplectic. Okay, you can check the PTVB or you can check the Calax paper. There's a very nice paper called the n-shifted symplectic, n-shifted cotangent stack is n-symplectic, something like that. For details, you can check that paper. So there is a symplectic structure defined by the Liouville one form. So there is a global one form of degree n, whose theorem will give you the symplectic structure. Okay. And actually, what you are going to do from the diagram, actually, so by using this diagram over here, you can observe the following. So you have actually other co-fiber sequences. So let me write it down quickly. For instance, if you look at the tangent complex of this fiber product, this is nothing but pullback of these two things, right? Plus projection I use 2, okay. T A1 N. Okay. So because of this fiber product diagram, the tangent complex of the one-jet stack is given by this direct sum. Oops. I guess I have. You are not seeing the screen, right? I guess I have some issues.
We see you.
Okay, just a minute. I have some kind of crash. Okay, let me reopen. Sorry, one not crash. Just give me a moment. Almost done. Yes. Okay. Let me share the screen. Okay, now you are seeing, right?
Yes.
Good. Okay. So what we were saying, now you have this identification, and therefore you have the following exact triangle and co-exact at the same time. Let me write it down. Okay, this one, this one, this one. Okay, we are just playing with these exact triangles. But if you look at carefully, now you have this natural map here. This is your natural map. And this is your co-fiber. which is just then, the invertible sheath. Therefore, you have this line bundle. So actually, these two things defines the pre-contact structure, pre-contact data. Okay. And next, you need to define some kind of a one form, which will play the role of contact one form. And you can define something like this. Define alpha to be d deram z plus lambda. And z is the variable, actually, I guess I forgot to write down. Z is the variable, to co-represent A1. Okay. So it's like A1 is just K spec of KZ co-represented by KZ. Okay. Therefore, you can define a one form like this. Maybe we need to use some pullbacks, under projection map, but I'm going to skip that part. So therefore, this is just a section, of this one jet stack. And sorry, section of this cotangent complex. And then you have a nice lemma you can prove. So the lemma tells you that if you look at the cocone of alpha turns out to be this thing, pullback of the tangent complex over the cotangent stack. So it's a little bit confusing, maybe, but something like this. And if you consider the relative tangent complex, the fibers, the vertical ones, so the vertical ones turns out to be the projection, the pullback under the projection of the tangent complex of this shifted affine line. Okay, so therefore this component is like a vertical component, and this is like horizontal component. Okay, so long story short, you can actually, because you need to show that the deram of this alpha is non-degenerate on the kernel. So somehow you can show this thing is non-degenerate on the cocone alpha, but this is true. Why? Because of the lemma, because of this observation. Actually, deram alpha is nothing but deram lambda, and this is omega, which is already non-degenerate on the cotangent stack, which is kind of a horizontal part of this construction. So therefore, this turns out to be non-degenerate. This is more or less the same kind of proof if you look at the classical setup. So therefore, you can say that, okay, this fiber product admits a natural N-contact structure. Okay, very similar to the classical setup. Since I guess I don't have that much time, the next section is kind of a little bit technical, so I'm just going to outline some basic facts. So you can also do the same thing, another big example, contact structures using geometric quantization. Okay, so this example is a little bit technical, so I'm just maybe going to state results very briefly. But the classical, let me just mention the classical idea. So the classical case, okay, classical symplectic geometry. So if you have, so for instance, this is your symplectic manifold, okay? And we assume the existence of a line bundle with a very particular connection, okay? Actually, this line bundle is kind of a complex line bundle. You have this projection such that the curvature of this connection is the symplectic form, okay? So you can assume something like this, or there is a nice obstruction. If this symplectic form is integral, it represents integral cohomology class, then there is a nice theorem. You can say that there exists such a line bundle with such connection with that property. Okay, this is called pre-quantum line bundle. Okay, so it's a complex line bundle. And then if you consider the associated principal bundle, so let's say this is your frame bundle, and you have a natural S1 action over here, and the projection is just the restriction of the original projection. So this is the associated S1 bundle. Okay. And then you have connection, and then here you have the connection one form. Okay. And if you look at the classical theory, you see that this guy turns out to be a contact form. Okay. So therefore, this total space here is a contact manifold. Okay. So, and the contact structure induced by this connection one form. So classically, we have this nice construction. So the question is, can we do this in the derived context? Okay. So the question is in the derived context. Actually, of course, to do that, we need the notion of a symplectic shifted geometric quantization. And Safronov actually introduced this notation, the notion of shifted geometric quantization. Okay, and it's a very nice and a little bit technical definition, but very the ad hoc way of. Let me just give you the definition, and you can feel what's going on. So I'm sorry, I don't have that much time, so I'm not going to explain the main ingredients, but here is the definition. So let's x omega be an n symplectic, n shifted symplectic derived stack. Okay, so by a pre-quantization, we mean, so it's pre-quantization is, now it's the technical part, is an n-gerb with connective structure. So we generally use this notation, okay, and such that the curvature, so the notion of curvature also, you can define this notion, is the curvature is your n-shifted symplectic form. Okay, so you have at least a similar kind of notion in a derived context, and the next task is try to do the similar trick over here. So you start with something, some kind of pre-quantization data, and obtain some kind of a line bundle. You consider a line bundle, and you just consider the corresponding U1 bundle, and in our situations, it's kind of a GM bundle. So let me just state the one of the theorems. Maybe I don't know, I don't have that much time for this, I guess. At least let me tell you this. The zero gerb with connective structure is exactly kind of a usual line bundle with connection. Okay, so therefore, this is a kind of a generalization of this discussion. So let me just at least tell you something like this. Let me just, if you consider, so let us consider the cotangent stack. As you see, this shifted zero cotangent stack. So therefore, it has zero shifted symplectic structure. And then somehow our theorem, so it's a kind of a black box over here. There is some hypothesis here. Let me just leave it as a black box. Somehow, by using certain results of Safronov, some results from Safronov paper, you can construct a particular GM bundle. Sorry, I have some issue with, oops, what's going on? Sorry, I have some issues with that. Okay, the screen. Sorry, at least let me just tell you there exists a GM bundle, okay, on this cotangent stack, okay, which carries zero shifted contact structure. Carrying zero shifted contact structure. Okay, so at least let me just state this kind of result. But the main idea is somehow we use the notion of, okay, there are some technical definitions like pre-quantum zero-shifted Lagrangian fibration structure. Okay, it's a little bit long story. Maybe next time I can discuss in more detail. But here in this black box region, so so you can use some nice results from Safronov paper and to mimic this procedure over here, as in the classical setup. So you have a very nice results, and then eventually you can construct a GM bundle on this cotangent stack, which has the structure of a zero shifted contact data. Okay, and you can produce similar kind of examples by just playing with and then applying the Safronov's results. For instance, you can do that for shifted and twisted cotangent stacks. It's also possible. And then you can just write down a very particular example. For instance, you can consider the moduli stack of flat G connections, and you can consider the moduli stack of G bundles, and there is a nice relation between these two. So applying a similar kind of construction, you can produce another GM bundle on, on the moduli stack of flat G connections, equipped with some zero shifted contact data. Okay, but they use very similar proof, but the essential tools coming from Safronov's results and using the tools from shifted geometric quantization, at least you can produce other examples of shifted contact structures. Okay, so let me stop here. So thank you.
Thank you very much, İlker.
Thank you.
So, any questions or comments? Maybe I will ask one question.
Mhm.
In symplectic geometry, there is this notion called Fukaya category.
Mhm.
Is there Fukaya category kind of thing in this derived setting?
Mhm. For the contact case, you
Yeah.
mean? Ah, I see. I have no idea.
No.
I don't know. It's a very, very good question, and have a very nice answer to that. But the good one, I don't know. Maybe.
Probably higher categories may enter into play.
Um,
Any questions or comments? Okay, so let's thank İlker once more.
thank you for having me.
Actually, I should say that İlker is speaking fourth time in our
Mhm.
seminar series, and we are very happy that he is contributing.
It's always a pleasure.
So maybe in this year we will have a week on higher structures and so on at Feza Gürsey Center for Physics and Mathematics, uh, where İlker will teach us about his theory on these things. Yeah, and we will be very happy. Yeah. Okay. So we will meet. Okay. By the way, 2 weeks from now, there is a national holiday, so there will be no seminar. So our seminar will be actually 4 weeks from now. And a speaker will be David Ayala from Montana State University. So uh, hope to see all of you there. And now I'm stopping